All right. So in order to understand how an elliptic curve cryptography works, we need to have some basic algebra. So I will briefly mention what a group, ring, and field is. So let's start with a group. A group G in algebra is a set of elements together with a binary operation star on G that combines two elements in G and form a third element in G, satisfying the following axioms. So as you can see, I'm defining a group with two things. First is a set of elements. The second thing is an operation. So it can be addition, multiplication, or anything. To give a general definition, I'm using the symbol star here. But when we say a binary operation, it means that it takes two elements from this set and produces an output again from this set. So this is what a binary operation means here. So we say such a set of elements and an operation is a group if they satisfy the following group axioms. First one is associativity. So here, as you can see, the parentheses shouldn't have any change in the result. So, this should be equal to this one. That is the idea of associativity. Second thing is the identity element. There should be an identity element here so that whenever you perform operation with that element and then any element in this set, the result should be again that element. Okay. So you might think that why we consider two different things like A operation E and E operation A. So for instance, in addition, it doesn't matter if you write 2 plus 3 and 3 plus 2, right? Those are the same things. The order doesn't change anything. So in groups, in some groups, the results might be different. And in some groups, this is identical. So in that case, we will call them abelian groups or commutative groups, but that definition will come later. Okay. So the third property that I want is inverse element. Okay. Every element in the set has to be an inverse. So by an inverse, we mean that B is the inverse of A if A's operation B or B operation A equals to identity element. Okay. So in order to make things more clear, let me give you an example. The set of integers and the addition operation is actually a group. Let's check. In order to prove it, we have to check if all of these axioms are satisfied. So let's start with associativity. So as you know, first summing B and C, then adding A equals to first adding A to B and then C. So associativity is satisfied. Identity element is as follows. 0 is the identity element. Since take any element from this integers A, add 0 to it, you will end up with again A. So we have an identity element here. Third thing is the inverse element. Do we have an inverse element? Yes. For every element A in Z, we have the inverse minus A because A plus minus A equals to the identity element. So here's a simple example for a group. Okay. Let's see an example where something is not a group. Instead of that, I will talk about Z star. This is a special notation because instead of talking the whole Z, we remove the 0 element. Okay. This is a notation where we say Z star. Okay. This is the Z minus the 0 element. So associativity is satisfied here. The multiplication operation is associative. We know that. We have the identity element because 1 is the identity. If you multiply anything with 1, you end up with the same number, right? But the thing is that we don't have the inverse element because for an element A in the Z star, the inverse should be 1 over A, so that A times 1 over A equals to 1. But the problem is that 1 over A is not in this set when A is different than 1, right? Because, for instance, if A is 2, in order to have the inverse, we should have 1 over 2, but 1 over 2 is not an integer. So this is why the integers with the multiplication operation does not provide you a group. So we have seen an example for a group and not a group, a set that is not a group with the multiplication operation. But as you can see, since 1 over A is not here, but it is in Q star, maybe I can increase the size of the set from Z star to Q star and check if it is a group or not. But in this case, it is a group, as you can guess, because associativity was already satisfied. One is the identity element again, but now every element has an inverse, because for any element A in Q or Q star, you have 1 over A. This is why we actually removed 0 here, as you can see, because if instead of Q star, if you consider Q, 0 is an element of Q, but 1 over 0, would not be here. It will be undefined. So this is why we remove the 0th element when we talk about multiplication most of the time. Okay. So these are basic examples for a group. But the thing is that since we are going to represent digital data as group elements, we mostly focus on finite groups in cryptography instead of infinite groups. So far, all of the examples I show you, integers, rational numbers have infinitely many elements. So let's focus on sets that have finite elements. So let's focus on Z4. I represented as Z4, which are the elements, 0, 1, 2, 3. But another notation for this would be Z divided by 4Z. For me, both of them are the same, but I'm going to use this notation. So let's check if it is a group. Associativity is satisfied because this addition equals to this addition modulo 2. The result is the same. There's an identity element because if you add 0 to anything, it will equal to A again, modulo 4, for any A in Z4. Inverse element, let's check if every element has an inverse. So 0 has the inverse 0, because when you add them, you obtain 0. 1 has the inverse 3, because if you add them, you end up with 0. 2 is its own inverse. 2 plus 2 is 0. And 3 has the inverse 1. As you can see this from here, because this is a commutative group. Okay, so every element has an inverse. So Z4 with the addition operation is a group. So only maybe strange thing you see is you were expecting probably 1 has the inverse -1, but -1 is not an element here. But if you add 4 to it, you end up with 3, and this is why it is the inverse. So question is, instead of plus, if I put multiplication here, question is, would it still be a group? Okay. But it might be surprising for some of you, but this is not a group, okay? So let's see why this is not the case. Associativity and identity element is obvious to see. Associativity works. Identity element is 1, it works, but not every element has an inverse. So let's see if 2 has an inverse. So here in this Z4 star, we have 3 elements, 1, 2, and 3. So multiply 2 with all of them, and you see that none of the result is the identity element 1, right? So this means that 2 does not have an inverse modulo 4. So this is why this is a counterexample showing that this is not a group. And actually, it is easy to see that 2 is not going to have an inverse in modulo 4 because 2 is an even number. So if you multiply it with anything, the result will be even number again. So when you calculate it modulo 4, it will be still an even number. It will never be equal to 1. So you might easily see that an element can have an inverse as long as it's relatively prime with this modulus. Okay, so 2 has no inverse in Z4 star because the greatest common divisor of 2 and 4 is not equal to 1, but it equals to 2. So question is, how can I make every element has an inverse so that this, so I can do it by making the greatest common divisor with any element in here relatively prime with the modulus. So if I choose the modulus prime number, then the problem is solved, right? So consider ZP star, but this time P is a prime number. So ZP star is the element starting from 0 to P minus 1. And our operation is multiplication. So associativity works, as you might guess. 1 is the identity element. Take any element from ZP star, multiply it with 1, you end up with A again, modulo P. But now every element has an inverse. I'm not going to prove it, but you have to trust me in this case, because since that element is relatively prime with P, if you multiply with every possibilities here, you will see that it has an inverse. So In finite groups or fields, we are going to work with ZP star most of the time, and this is one of the reasons, because for multiplication it is a group. Okay, so let's continue. So let's talk about the generator of a group. G is called the generator of the group G if every other element of the group may be obtained by repeatedly applying the group operation to G. So it might sound strange, but I will give an example. And since we are talking about additive and multiplicative groups, the notation is as follows. Each element can be written as a power of G in multiplicative notation, and each element can be written as a multiple of G in additive notation. So it will make sense in our example. So, for instance, let's consider Z7 star with multiplication. We already showed that this is a group. And the question is 2 is a generator of this group? Okay, so let's check. So 2 to the power 1 equals to 2. So I'm repeating the group operation, right? In this case, it is multiplication. So I multiply 2 with itself, which is 2 to the power 2. I end up with 4. I again multiplied with 2, which equals to 2 to the power 3. But this time I end up with 1 modulo 7. So actually, when you reach the identity element, this means that you actually find the order of your element. So this means that the order of 2 is 3, because after 3 operations, you end up with the identity element. If you continue, you have to multiply this number with 2. But since you have the identity element here, this means that 2 to the power 4 equals to 2, right? Which is already here. 2 to the power 5 will be 4. So you are actually making a cycle here, see? But the problem is that I calculated these powers of 2, but I couldn't obtain every element in Z7 star because I couldn't see 3, 5, or 6 here, okay? So since 2 is not a generator of this group, let's see a generator of this group. Let's see if 3 is a generator, and actually it is. So here, as you can see, if you calculate every power of 3, you end up with every element in Z7 star. So here you hit the identity element. If you continue more, you will be repeating these numbers again, okay? So this is actually referred to as the order of that element. So from this slide, you can see that 2 has order 3, and 3 has order 6. Since Z7 star has 6 elements, this is why it is the generator, okay? And a generator may not be a unique element, so there might be other generators in this group, okay? There may be something other than 3 which also generates the group, so you need to check, okay? A generator of a group is important because in the Diffie-Hellman key exchange, my first sentence is saying that let G be a generator of that group, okay? So in elliptic cryptography, we will also need a generator. Okay, I already gave this definition, but let's repeat it again. A definition of an abelian group or a commutative group is as follows. A group G is said to be abelian or commutative if X operation Y actually equals to Y operation X. So order does not change in abelian groups. Of course, this should be valid for every XY in this group. Okay. So with this definition, we can move on to the rings. We talked about groups. Now let's talk about something with 2 operations. So a ring R in algebra is a set of elements together with 2 binary operations plus and start on R satisfying. Actually, you can use the multiplicative notation here. It doesn't matter, but all you need to know that it supports 2 operations, 1 addition and 1 multiplication, let's say. So it has to support the following. R is an abelian group under addition. So far, this is what we talk about, abelian groups. But it should also satisfy for the second operation, the associativity, okay? And it should also have the distributive properties between these 2 operations. So like A star B plus C would be A star B plus, okay, there is a typo here. This should be A star C. Sorry for that. The similar thing is shown below. So if you multiply B plus C star A, you end up with B star A plus C star A, Okay, again, this should be star, sorry for the typo. So with these two operations, we can define rings. Consider Zn with respect to these two operations, addition and multiplication. This is a ring. And the integers again with plus and addition and multiplication are also rings, because as you can see, for the addition operation, we require it to be a group. But for the second operation, we don't ask it to be a group. So we don't ask the inverse elements in multiplication, but we only ask for these operations, okay? And they are valid. So rings are somewhat different, but as you can guess, if I'm not expecting multiplicative inverses here, when I expect multiplicative inverses, I will tell them something else, so I will call them a field. So let me give you the definition of a field. A field is a set F which is closed under two binary operations plus, addition and multiplication. So I'm asking F to be an abelian group under addition, and I'm also asking F star to be an abelian group under multiplication. So here's an example. If you consider ZP, where P is a prime, with respect to the addition and multiplication, this is a field. And most of the time we represented it as FP. Sometimes people call it Galois field P. And you might ask that in finite fields, what are the number of elements, or what are the finite fields so that I can count the elements? Actually, you can have finite fields with element Q if Q is a prime power. And then there's essentially only one finite field of order Q, which is denoted by FQ. So this is important. So if you choose Q as a prime number, most of the time we say P, so we call it FP and say that this is a field, but it doesn't have to be a prime number. It can also be a power of a prime. So there is a field with two elements, F2, but there's also a group with, a finite field with four elements, which is F2 to the power 2. Okay, or we have a field with 8 elements, which is referred to as F2 to the power 3. But one thing to be clear about this, when we talk about the field with 4 elements, I'm not talking about Z4, okay? Because Z4 is not a field. You have to be very careful about this. Sometimes there is a misconception about it. Since there is 4 elements and since we have Z4, people think that Z4 is a field. No, Z4 is not a field, but I can create a field with 4 elements, okay? Because 4 is a power of a prime, which is 2 to the 2.